Hello, and welcome to Still Behind the Bench. My name is Adam, and on this channel I will attempt to describe the science behind distilling spirits in a more technical way. Hopefully it'll whet your appetite to learn more and teach you enough so that you're more self-sufficient. So for this video I'm going to be talking about active versus passive reflux, vapor-liquid equilibrium, plates, packing, and potential output. Let's get started. Vapor-liquid equilibrium can be a super complex topic, but I've whittled it down into just what we need to be aware of. It's essentially why distillation works, and I'll only be focusing on water and ethanol. So due to multiple properties like temperature, barometric pressure, vapor pressure, solubility, bubble point, dew point, different compounds in this non-ideal mixture, and it's non-ideal because it doesn't follow Raoult's law, will have different concentrations in the liquid compared to the vapor. The concentration of water and the concentration of ethanol in the liquid will be different than it is in the vapor. VLE is studied in a closed system, but since we are continually taking off that vapor, it will continually be replaced or replenished at ever lowering concentrations. For example, a 10% ABV liquid will produce a 54% ABV vapor, and a 9% ABV liquid will produce a 51% ABV liquid or vapor. This leads me to what are called VLE charts and graphs. Traditionally, VLE data for water-ethanol mixtures needed to be experimentally derived. Since it's non-ideal, it couldn't just be easily calculated. After tons of experiments that scientists did, after they collected all their data, and most importantly, they shared their data, numerous methods of calculating VLE cropped up. Experimental data sets still exist though, and they still rule the land. I had access to one such data set, and so I produced my own charts and graphs. I have an absolute chart, like this one here, and then I have a chart rounded to the nearest 0.5% ABV. I also quickly made this graph just to show the difference visually show the difference in liquid vapor ABV changes, and also to show how it flattens out in your azeotrope. Links for these two charts are in the description. So I'm going to use the rounded chart just because it's easier to use. So looking at the chart, you can see, I hope you can see, that approximately a 10% ABV will end up with an approximately 54% vapor. When that vapor condenses, its liquid will be at 54%. And when that liquid evaporates, its vapor, as you can see if you go to the second page, will be at around 81%. And so on and so forth. As you get closer to azeotrope, you can see the difference between the liquid and the vapor gets smaller though. And what happens at azeotrope is that the concentration of the liquid, or the concentration in the liquid, and the concentration in the vapor become the same, and you can't go any further than that. When talking about alcohol by volume, that azeotrope value is 97.2%, and when talking about alcohol by weight, that value is 95.6%. So this VLE process essentially revolves around a process called refluxing. Reflux at its most basic is the process of evaporating a liquid, then condensing that vapor back into a liquid and letting it drop back down into the liquid it originally evaporated from. In spirit distilling, we talk about an added step. Upward moving vapors will put heat into the condensate and re-evaporate some of those condensed liquids into a new vapor with different characteristics. So if we start with a 10% ABV wash, it'll have a 54% ABV vapor. When that vapor condenses on the walls of the still, it'll also be at 54% ABV, and then upward moving vapors will heat that 54% liquid, and it will evaporate, leaving or releasing an 81% ABV vapor. So you'll have those 54% ABV vapors from the wash mixing with the 81% ABV vapors from the refluxed condensate, giving you something that sits in between those two values, typically speaking. This leads to the ideas of passive reflux and active reflux. They're both pretty simple concepts. Passive reflux, which is the only type of reflux that happens inside a pot still, is where the vapor condenses onto the walls of the still and travels back down towards the wash. The larger the headspace, the more passive reflux you'll have. With an upwards facing line arm, you'll also have more passive reflux happening. And in both cases, with more passive reflux, you get more separation. And so you may end up with a less flavored and less odorous distillate. Not a huge amount of difference, but it will be noticeable if you tried to compare the two. Active reflux, on the other hand, requires you adding extra components that induce reflux, like packing, like plates, or like a reflux condenser. These components either add additional surface area for vapors to condense on and for that condensate to come into contact with more upward moving vapors, or the component will add a continuously cooled surface with the purpose of controlling the amount of vapor that it allows to pass by it. You can then connect the packing or plates back to the VLE chart. Here, with the plated portion of my column, you can see there would be 4 plates in it. Using the VLE chart, we can see I go from, say, a 10% ABV wash. Inside the boiler itself, the vapor above it would be about 54%. So that means the liquid at the bottom of the first plate would be at 54%. The vapor above it would then be at 81%. That means the liquid at the bottom of the second plate would be at 81%. Then we go from 81% to 87.5%. That means this will be at 87.5%, and this vapor above it will be at 90.5%. Then this liquid will be at 90.5%, and this will be at 92%. Then if I have a plate up here at 92%, the vapor above it will be at 93%. And so just with these 4 plates, I can get all the way up to, or sometimes 5 plates, all the way up to 93%. If I then add a packed column on top of it, I can go all the way to azeotrope. With a packed column, on the other hand, something like this, you need to know what's called the Hetp, or height equivalent theoretical plate. It's essentially a value that tells you what height equals 1 plate. So with this specific piece, I can add about 1.6 liters of 5mm copper spiral prismatic packing. And I'll go into what SPP is a little bit later. With 1.6 liters of copper SPP, I get it between a 27mm and 30mm Hetp value. So that means for every approximately 30mm of height, it's equal to 1 plate. So for this entire column, I can get about 11 to 12 plates worth of packing or of column separation. And then I can just look on my chart and make, I guess, about 13 jumps, because you get 1 jump for the pot. So again, starting at 10%, you go to 54%, and then you just go back and forth 12 more times, and you get to azeotrope with just this small piece. However, you also have to take into account the rate at which you put vapor into the column, so how much heat energy you're putting into the boiler. If you put it in fast enough, the vapor won't have enough time to reflux properly as it goes up. And with just a short column this small, I typically don't have enough time to sit around and run it really slowly. So I'll use this in combination with actual plates to get to azeotrope if I want to get that high. There are probably lots of different types of ways you can make plates, but I'm only going to talk about 2. And there are numerous different types of packing, but I'm only going to mention a few. With plates, generally speaking, hobbyists really only deal with 2. You have perforated plates and bubble cap plates. With bubble cap plates, which I have an example of here, just a steel one, it's just a regular plate with these 3 caps on it and another which is called a downcomer. So essentially what happens is that vapor will come up, pass through the holes in the bottom, it comes up and over what looks like a weir on the inside, and then it comes out these little slots in the bottom. Once it gets out here, it is usually condensed back into a liquid. This plate will then fill up with liquid until it gets over the edge of this downcomer, and then it'll start dropping back down. At the same time, these caps have typically heated up to the point where they won't condense any more vapor, but they will allow the vapor to come out these slots and bubble through the liquid. It gets quite vigorous, and that's why they call these bubble cap plates. That vapor will condense inside the liquid until the liquid's warm enough that it starts evaporating as well, and it all moves up to the next plate. Perforated plates look very different from this. They're essentially just this plate with a whole bunch of little holes drilled into it. And then what happens is the vapors will come pass through that plate, and they will condense on the walls and the bottom surface of the next plate and drip back down. It will fill this plate because there's enough upward pressure to keep a liquid on this plate. And then that vapor will also bubble through those little holes in the plates. And that's how reflux happens with the perforated plates. With packing materials, there are numerous ones that hobbyists use. Stainless steel scrubbers, pure copper scrubbers. Some copper scrubbers are actually plated. You don't want to use those because the copper plating comes off and then all you have is a big pile of rusty metal scrubber. So pure copper scrubbers. Pure copper mesh is really popular as well. This stuff, it's what I am using now until I can justify buying more copper SPP. Copper SPP is expensive. SPP stands for spiral prismatic packing. So essentially, and I'll put a photo up, it looks like a triangular spring, so like that. But imagine that every other loop is rotated 90 degrees. So it looks like a six-sided rounded star. That's just to maximize surface area. And personally, I find that they have the greatest packing density, while also not allowing a huge amount of flooding. So you can get those in stainless steel or copper. There's also just regular spiral packing, which is essentially just a spring. You can also get those in stainless steel or copper. There's Rashik rings, which look just like a small ceramic tube, glass tube. Sometimes they're metal. Paul rings, interlocks saddles. They're just, they look like a saddle, like a horse saddle. You can get them in ceramic or metal. Glass marbles used to be really popular. And a more semi-recent addition was lava rock, sometimes called scoria, because of all the surface area, because of all the pitting that happens. I myself have only ever used copper SPP, copper mesh, and copper or stainless steel bubble cap plates. For packing, I prefer the SPP over the mesh, simply because it's more consistent from run to run. I know that I'm adding the same amount of copper SPP each time, and I know that its packing density will generally be the same each time. Whereas with the copper mesh, I have to wrap it myself each time. So there will be inconsistencies from run to run every time I pull it out and put it back in. When I wrap my copper mesh, I make sure to make it tight enough, or I should say make it loose enough so that it will hold itself in place, but I also make it tight enough so that when I blow through the tube, there's a small to moderate amount of effort required. If there's no effort required, I find that it's too loose and not enough reflux happens inside it. And if it's too tight, then flooding will happen. And flooding is just when the amount of space for the condensed liquid to drop back down isn't high enough, and the upward moving vapors can hold the liquid in place. So essentially reflux stops happening, and what liquid does turn back into a vapor doesn't really reflux anymore, and the distillate ABV essentially just stops. So yeah, a small to moderate amount of pressure when trying to blow through it, or effort, is essentially how I gauge the copper mesh. Then we get to reflux condensers. A deflegmator is a common type of reflux condenser. The more common designs lately are called tube and shell or a shotgun design. You'll essentially have, and I can actually show you, let me just grab this condenser here. All right. So the shotgun design essentially has a bunch of smaller tubes on the inside. You can see here, smaller tubes on the inside, and the coolant will run through the jacket on the outside. This is my product condenser though. So a reflux condenser will be at the top of the main column. Another type of reflux condenser is just this. This is what I have for my still, CCVM style. Essentially with this and with the deflagmator or any type of reflux condenser, you essentially just run coolant through it, and you use that coolant to knock down all the vapors at full reflux, and then you change the action. So with a deflagmator you might slow down the flow of coolant through it. With this type I have a constant flow, and I move it up and down in front of the point of no return. This way I can control how much vapor will be able to pass by it. So I don't know if you'll be able to see this, but we will. I know what I can do. Hold on. Didn't think I'd be taking everything apart for this video, but so you can see the coil in there. So I can just move it up and down and control how much vapor I want to allow out through here into the product condenser. Sometimes if I'm doing a really fast run, I'll also have to put some copper mesh or a copper scrubber in amongst the coils of that condenser. And I'll put a link in the description from where I got it. It's just, what's it called? Corrugated stainless steel tubing. It's meant for, I think, natural gas connections between like a stove or a dryer. And then, yeah, with a deflagmator, like I said before, you would just slow the full flow of coolant, or if you wanted to kill all reflux, you'd just turn the flow of the coolant off altogether and all the vapors would pass by the deflagmator. That leads us to, how much liquor am I going to get anyways, right? The potential output, that's what we want to know. Let's go to the board because we have to do a little bit of math. All right, so here we are at the bench. Before we get onto the potential distillate or potential output, I wanted to take a quick look at the chart just to give a simple explanation of how you use it. It'll be pretty obvious once you see it. This is the liquid percent. This is the vapor above it. So 10.5% gives you roughly 54%. 21% gives you 69. 38 gives you 76.5. 40% gives you 77%, and so on. It's pretty easy. Just 3 pages. It's not perfect. Sometimes it might be a little bit off, typically because of passive reflux. It's hard to predict how passive reflux will act, or how much passive reflux and where it will happen in your still. Generally speaking though, I've found that you never really get above 84% with a simple pot still though. Okay, so we'll go on to potential output now. So the first thing you're going to want to do is essentially make a guess on what the max distillate ABV is going to be. So with the regular pot still, you'll never get above 84%. So the longer your line arm is, or your output, the more passive reflux you're going to have. The bigger the headspace, the more passive reflux you're going to have. But let's just say, for instance, that the output was going to be, or the max distillate ABV is going to be 75%, just to make an easy number. So we will say, no, here, we'll call it max distillate ABV. You'll need to know your initial wash volume, VW, the wash ABV, and you'll need to know your ethanol recovery efficiency. I would say just in the beginning start with recovery efficiency. Start with 80%. Just because we want that to be 75, don't we? It's a good number to start with. You'll typically get more than that, but 20 or 80% or 20% losses is a good place to start until you know how your still works, how the wash that you've just made acts in the still. A loss of 20% will be to the heads and the tails, if you're wondering where that other goes. So let's say the wash volume was 50 liters and the wash ABV was 10%. Oops. Dry. 10%. So the formula is like this. So you have your initial wash volume times the wash ABV times the recovery efficiency, and you'll divide that by the max distillate ABV. And this will give you we will call it distillate volume. So we know what these values are. They were 50 liters times 10% times 80% recovery. We're dividing that all by 75%, and that is going to give us roughly 5.3 liters of distillate at 75%. So 5.3 liters of hearts plus maybe a bit of tails and a little bit of heads at 75%. For my friends in the US, 50 liters is approximately, what would it be, around 13 gallons, I think. So 13 gallons times 0.10 times 0.80 divided by 0.75. That gives us approximately 1.39 or 1.4 gallons or 5.5 quarts, which is not too bad, not too shabby. That's essentially how I estimate what my potential volume is, or potential output is going to be. If your recovery efficiency will typically be higher than 80%, and if that goes up, this goes up, your distillate volume goes up. But if your potential or your max distillate ABV goes up, so the ABV of this, if that goes up, then this number will typically go down. And I'll explain why. The part in the brackets is essentially saying how much pure ethanol did I recover, right? So how much pure ethanol, these parts are how much pure ethanol is in the wash, how much of that pure ethanol did I recover, and then as you're saying, if I dilute that pure ethanol down to this percent, what is the volume? That's essentially how this breaks down. And I'm usually pretty close. I find most of the time I'm typically within half a liter to this number, but that just comes with experience, knowing generally how my still works and what the potential max ABV will be when I distill it in pot still mode. When I'm doing it in reflux, column filled with mesh or SPP, recovery is usually up around, I'd probably say 95%. And then my distillate ABV is typically around 96%. So my end volume is typically lower than this, but it's a more pure product. And that's it for this video. If you want to see more videos like this, please click like and subscribe, and have a great week.